All right, so last week we had done half of example number 26 with the National League data. So we need to finish this problem before we move on to the next stuff. So the next part was actually looking at the American League and calculating their variance and standard deviation. So let me pull up that problem that we were working on last week. Okay. So we had looked at the National League. We calculated the midpoint and then multiplied the frequency with the midpoint. And then we actually took the square of the midpoint and then multiplied it with the frequency. So we completed these columns. And then using our formula, we were able to come up with variance and standard deviation for the National League. So we basically want to repeat that process with the American League. So the first part would be calculating the midpoints for the American League. So let me go ahead and pull up that example again. So go ahead and calculate those midpoints if you haven't already done that. And again, keep in mind that you do not want to round any of your intermediate answers. You want to leave them as many decimals as they are, because if you start rounding now, then your standard deviation will be incorrect. Okay, so what do we do to find the midpoint again? Very good. Add the two class limits and divide by 2. So adding the lower and the upper class limit. Alrighty, so let's see what these numbers come out to be. Okay, and then our last one. Can somebody verify these numbers for me, please? I've got 0.2465, 0.2525, 0.2585, 0.2645, 0.2675, and 0.2765. Yeah. All right. Okay. Okay, so your next column, if you're done with the midpoint, is going to be multiplying just the frequency with the midpoint. So no squares, nothing, right? Directly F, which is your frequency column, multiplied with the midpoint. So the last one's going to be easy since it's zeros. This guy here will be 0.2645 since he's multiplied by 1. Okay. Yes.
I don't know if I'm just doing this wrong or not, but I'm getting a different midpoint for the class of 0.268 to 0.27.
Oh, the second to last?
Yeah, it's
Point 2705.
What did I do?
67.
I did 262 instead of 268. Okay, so 0.268, 0.273 divided by 2705. All right, thank you guys. And then multiply that by 3, 8115. Okay. Were the others okay? Yeah, okay, wonderful. For the last column, what's your process going to be for calculating those numbers? Go ahead. Square which value though?
The mid value, the other one, the F times XN. The one we just did.
No. Are you talking about squaring the column we just completed?
Yes.
No. You do not square this column to get this answer.
You square the midpoints and multiply by the frequency.
Yeah, so that's the important part, because if that's the step we make a mistake in, then all our calculations following that is going to be incorrect. So this guy is saying actually start by taking the midpoint, square it, and then multiply with the frequency. So take this number, square by itself, whatever answer you get, then multiply with it. Does that make sense? Anybody else confused about that column? Because remember how we were talking about this is all a interconnected process. So if we make a mistake at this stage, all our following calculations are also going to be incorrect. So you are going to take 0.2465, square that number, and then multiply it by 3 to get your very last column. So this guy comes out to be 0.18228675. Then you're going to do 0.2525 squared multiplied by 6, which is coming out to be 0.3825,375, and so on, right? Joseph, are you done with that column?
Yeah.
Okay.
I don't think I did it.
Why do you think that?
I got a different answer for that one.
Okay, let me come in.
And take this. So you take this, multiply or square it. It's weird because the homework I did the other way and I got all the answers right.
And then times it by the frequency.
Anybody else not getting these numbers? Okay, so the next one is going to be 0.2585 squared and then multiplied by 2, which comes out to be 0. Okay, then we've got 2645 squared, and that's just multiplied by 1. So this guy will be 0.06996025. Again, remember you are only using the midpoint column. What's going to happen on the last value?
0.
Yeah, since your frequency is 0, even if you square that midpoint, it's just going to come out to be zeros. You don't have to write that many zeros. I'm just trying to match the decimal places. Okay. So looking at the national lead, what should be our next step here? What else did we do with this table? Yeah, so you need to find the total of the frequency column, the frequency times midpoint column, and then the frequency times the square of the midpoint. So let's start with the frequency. What's our total for F? 15. Very good. For frequency times midpoint, the second to last?
I got 3.8475.
3.8475. Okay, so that's about 2. That would be about 3. Yeah, I can see that. Okay, do you have the last one?
Yes. 0.98793975.
Okay, slow down.
0.98793975.
79, 39, 75. All right, as always, I would need somebody else to confirm those totals for me, please. So, especially for the last two, because I can do the frequency. 3.8475 for F times XM. Yeah, okay, wonderful. And then the F times X sub M squared column, 0.98793975. Yeah, all right, wonderful. Okay, once you get those totals, then we're ready to use these calculations. And this will be for the American lead, starting with our variance, which is n times summation the frequency times x sub m squared minus the summation of f times x sub m, the whole quantity squared, divided by n times n minus 1. So our n is 15, right? And again, you'll need to go back to the column here. This number here is 9879. Oh, what happened? Oh, there we go. Okay, so just bringing those values from our table to our formula. So now we are looking at 0.98793975 multiplied with our n value of 15, which is 14.81909.625. And from that, we are subtracting 3.8475, which has to be squared first, right? And that's coming out to be 14.80 3, sorry, 80, 325625, and then you're going to be dividing this by 15 times 14. Okay, so remember what I told you guys last time also, the numerator values should be close enough in proximity. If your numbers are coming out to be too far apart, then of course our calculation went wrong, because it's very rarely that you will have a big difference between those two quantities when you get the answers on your numerator. So now from that I need to subtract. And I am getting a numerator of 0.01584 divided by . And again, like we saw with the National League example, you should see a pretty small number showing up here. So I've got 0.000075429. Now, when you're calculating your standard deviation, make sure you're not rounding this answer. Keep it as it is. Our raw data was 3 decimal places. So this guy should actually be 4 decimal places. So you're getting a variance of 0.00075, a standard deviation of 0.0087, and this is for the American League, right? And then for your National League, which was the calculation we did last week, you got a variance of approximately 0.000050 and a standard deviation of 0.0071. Again, since our raw data is 3 decimal places, we're rounding these numbers to 4 decimal places. So if you had to do a comparison, and we were talking about batting averages here, what would you say about the results between the two leagues? Looking at their variance and standard deviation.
So there's less variance between the National League than there is in the American League.
Yeah, because you do have a slightly smaller number for the National League, but how much of a difference do you think it makes at this point when you're looking at 0.0071 and 0.0087? Negligible. Yeah, I mean, you could probably say that they are comparable to each other, but if we had to, we would of course pick the smaller standard deviation, because again, remember, smaller standard deviation tells us you are more clustered closer, right? You're not spread out as far apart, but just the way these values came out to be, you're not seeing a big difference between the two leagues. So So something like that could be your conclusion. That their averages are comparable, but the National League is just slightly better than the American League. Okay, so this was basically an example where we were trying to see how standard deviation and variance works with grouped data, right? So instead of having just single values, you are looking at those classes when you're trying to calculate this. So any questions on this example? And what about the process of going through the calculations? Any questions on that? Okay, so the one thing you really have to remember, which as some of you pointed out, was calculating that last column, right? With the x squared of the midpoint multiplied by the frequency. So remember, you're always working with this column, the midpoint column, and the frequency. We never come back and reuse this to calculate our last column. So the f times xm column, or the frequency times midpoint column, will stay untouched. We are basically just interested in those totals, but it's not involving the calculation of that last column. So just be careful about that. Alrighty, so let's get back to our handout here. And we had looked at example on page 10. Okay. So the measures, yeah. Oh, you don't have the handout? Okay. Okay, so just as a summary of the different measurements we have seen for variation or dispersion, as they're called, you have your range, variance, and standard deviation. Again, remember that when you are using population, we use the Greek letters. When you're using a sample, we use the English letters or Roman letters. And this one here is just kind of going through the uses, as you can see, of variance and standard deviation. So just quickly, remember, we are talking about variation or dispersion, so we are talking about the spread of the data. So the larger your values will be for variance and standard deviation, the more spread out or dispersed your data is. Of course, we want them to be closer, and especially closer towards the mean. You can also think about using these calculations for looking at the consistency of your variable. So even for the same variable over time or over different samples, you can kind of see, is it going to stay the same? So like here they're talking about the manufacturing of fittings such as nuts and bolts. Obviously the idea is you want that variation to be as small as possible, right? Because the idea is if this is the measurement for your nuts and bolts, so over that manufacturing period, that should obviously stay the same. You don't want those values to keep changing, because if your variation increases, that means your machine's not working properly, right? Something's going wrong. So you can think of that as quality control. We are also actually talking about, you can use your variance and standard deviation to determine the number of data values that are going to fall within a specified interval. So we may want to know if our mean is, whatever that value is. If we just go one standard deviation away from the mean, so maybe one standard deviation below the mean and one standard deviation above the mean, what percentage of our data value is going to fall within that range? So we are actually going to use Chebyshev's theorem, which I think we're going to do it either in this section or the next one. And we will actually also introduce the bell-shaped distribution as well. So they are saying Chebyshev's theorem actually works with any kind of distribution. You don't have to have that symmetrical bell-shaped distribution. It works with everything. And the idea is 75% of the data should fall within 2 standard deviations. So if you're just going 2 standard deviations away from the mean, and that's below and above the mean, you're looking at 75% of your entire data value that's going to fall within 2 standard deviations. And of course, we talk about variance and standard deviation in inferential statistics also, and we'll definitely get to that as we move forward. So the first thing we actually want to talk about is the coefficient of variation here. So you can kind of see in that little paragraph here, we're talking about this example. Suppose an automobile dealer wanted to compare the standard deviation of miles driven for cars she received as trade-ins. So for a specific year, the standard deviation for Buicks was 422 miles, and the standard deviation for Cadillacs was 350 miles. So basically, we are saying that the variation is greater. Yeah, the variation was greater in the Buicks because that's at 422 as compared to 350 miles, right? And we're talking about if your mean was, you know, whatever, I guess they're not really telling us what the mean for these vehicles is, but whatever was the mean, if you're going that far out, then does that make sense to go for a vehicle that has such a large standard deviation? But they're saying, what if a manager wanted to compare the standard deviations of two different variables, where the number of sales per person over a 3-month period and the commission made by a salesperson. So, you know, when you're comparing mileage to mileage, that's an easy direct comparison like we were doing with our American League and National League. But coefficient of variation actually comes into play in a situation like this, where you are comparing the number of sales you have made as a salesperson and the commission you have earned. So how would that be? So that's actually where this idea of coefficient of variation, or C bar, comes into play, is because you can now take different measurements and still come up with a calculation. And as you can see, you've got your S, which is for standard deviation. You've got your X bar, which is the mean, right? And then you're multiplying that with 100. Again, difference between population and samples. So just a quick example here. Again, we're talking about the sales of automobiles here. So over a 3-month period, the mean number of sales for cars was 87 cars. They're telling us the standard deviation is 5. And the commissions based on that was, your mean value is 5,225 and the standard deviation is 773. So we have the number of sales and we have the commission the salespeople earned, right? So you will take each variable. We're starting out with the number of cars. So they're telling us the standard deviation is 5. The mean is 87. Multiplied by 100, you're getting 5.7% of your sales happen there. With the commission, your standard deviation is 773. The mean for the commission is 5,225. Again, that comes out to be 14.8%. So again, you can see we have a larger percentage value for the commissions. So again, based on that, we can say the commissions are more variable than the sales, because again, you're comparing standard deviation based on the mean, and then you're trying to see, you know, which was more variable. And what do you think makes that commission more varied than the number of sales of these cars? I mean, if they were getting the same amount of commission for selling cars, shouldn't those values have been approximately the same? Price of the car, is it a luxury model, is it a standard model, right? Because based on what kind of car you sell, your commission is based on that. It's never a standard commission that if you sell one car, this is how much commission you get, because if you're selling a lower end model, you're not going to get as much commission. But if you sell maybe a whole, you know, souped up every feature that's possibly available, the more money you get the customer to pay, the higher your commission is going to be. So that's why your commission coefficient variation came out to be higher. Okay, here we're talking about roller coasters. So the mean speed for 5 fastest wooden roller coasters is again 69.16 miles per hour. And they're actually giving us variance this time. Variance is 2.76. The mean height, so you're comparing speed and height, right? The mean height for the 5 tallest roller coasters is 177.80 feet. And again, your variance for those is 157.70, and they're again asking us to compare the two data sets. So the first thing you should obviously notice is they're giving us the variance and not the standard deviation. So you need to calculate your standard deviation before you calculate the coefficient of variance. So that's why you will notice these guys have square roots on them, because that's how we calculate standard deviation. And then you are getting 2% from the mean speed, or the speed of the wooden roller coasters, and you are getting actually 1% from the height of the tallest roller coasters. So again, you have the higher variance for, what was that, the speed, right? So again, you can say that one is a little bit more varied than the height of the tallest roller coasters. Okay, so let's do a quick example for the variance before we come back to range rule of thumb. Okay, how about number 27? The average number of days that construction workers miss per year, and their standard deviation is given to you. So the average number of days is 11, the standard deviation is 2.3. The average number of days that factory workers miss per year is 8, with a standard deviation of 18. So they want to know which class is more variable in terms of days missed. So they are giving us a standard deviation here, right? And they are giving us the mean. So let's do the C variance for construction workers. And remember that standard deviation divided by the mean multiplied by 100. That was 2.3 over 11 multiplied by 100, and what does that come out to be? So 2.3 divided by 11 multiplied by 100. 20%. Okay, which will be approximately 21%. It looked like they were rounding it up to whole numbers for all of that. And then for the factory workers, they were telling us the mean or the average is 8 with a standard deviation of 1.8. And what did this guy come out to be? 22.5. Very good. So which set is more varied? Yeah. You know, again, you can make the argument that the numbers were still pretty close to one another. Again, I know 23 is larger than 21, but again, it wasn't like you got 15 and 23, which was a big difference. So they are still pretty comparable to each other if you look at it that way. Okay, so remember, basically the idea with coefficient of variance is when you have two values that are not using, that are not using the same measurement. Usually when your variables are completely different, you can use this comparison. Now in this example, we were still honestly talking about number of days. So your variables are pretty similar, but the only difference was one set was for construction workers, the other set was for factory workers, right? So that was really the only difference. But again, that kind of gives us a good idea of what kind of variance we are looking at. Now, the idea behind range rule of thumb is it's actually an approximate way of calculating your variation, standard deviation. So it's just a very, very rough approximate way. And you can look at that and you can see you're basically just taking the range of your data value and dividing by 4, right? I mean, we're not going through all of that big calculations that we looked at or even using the shortcut method. We're literally just taking the range and dividing by 4. And this idea is just to get a ballpark figure of what our standard deviation will be like. But then if you need a better accurate answer, you of course want to go through the process of finding your standard deviation. So again, just a basic example underneath that box, you've got your data set of 5, 8, 8, 9, 10, 12, and 13. So if you did the standard deviation using the formula, you're going to get 2.7, but then using our range rule of thumb, you can see with the range rule of thumb, it comes out to be approximately 2, right? So again, 2.7, and you're getting a value of 2. So you're going to be nearby, but not an exact answer. And this is obviously just to get an idea. If you're trying to do some kind of rough calculation and you just want to know what that standard deviation would be like without getting into details, this is a good way to go about it. Now, right in the middle, it talks about a note of caution here. So be very careful when you're using this. This is literally just an approximation and should be used when your distribution of data values is unimodal and roughly symmetric. Because if you have a roughly symmetric data distribution, you are going to be more closer to the actual standard deviation. Then remember, the idea with unimodal is there's only one value, which is your mode, right? Bimodal would be 2 values are your mode. So that means you would have data probably not symmetric if you had a bimodal or multimodal distribution. But if you have unimodal and it's roughly symmetric, you're kind of thinking of that bell-shaped symmetric curve, which means your standard deviation is going to be more closer to the accurate value than otherwise. And again, they're talking about using the range rule of thumb to estimate your largest and smallest data set. Now, the smallest data value will be approximately 2 standard deviations below the mean. And of course, the largest data value would be then 2 standard deviations above the mean. And they're telling us if you found the mean of that data, it comes out to be about 9.3. So they're actually showing you how you can calculate your smallest and greatest data values based on this range rule of thumb. So you've got your mean and you've got your standard deviation, that S value, right? And then we are saying approximately 2 standard deviations below the mean. So that's why we're subtracting. You're going to be at 5.3. Approximately 2 standard deviations above the mean, you're going to be at 13.3. So go back and look at that data set. Our smallest value was 5. Our largest value is 13. So again, this idea of range rule of thumb can help you come up again with approximate values, right? Because we were at 5 and 13, you're getting 5.3 and 13.3 as your lowest and highest value. So these are basically just an idea of getting an approximation. You probably don't want to base your calculations on these, right? This is just to give you a quick idea of what's going on. I'm actually not sure if they give us an example on range rule of thumb. Because this is where we're getting to Chebyshev's theorem. Not really. But do we understand the general concept of range rule of thumb? Everybody okay with that? Any questions?
Why would we use that?
Just to get approximations without having to do the longer calculation. So the idea is if you just quickly wanted to know, if you were comparing something offhand, where you wanted to know which data set is more varied, but you didn't want to go through the whole calculation of finding your variance and then finding your standard deviation, you could use range rule of thumb. So again, if you go back to our example of, which it really wouldn't be a good example since these guys were so close, but if you were trying to figure out which data set is more varied, then you could use that idea here, like we were comparing the batting averages for National League and American League. But in this case, like I said, it's not going to be very helpful because you saw how our standard deviations were so close to each other, right? 0.0071 and 0.0087. But if you had something like this and you just wanted a quick calculation, that's where you would bring in the range rule of thumb. And then, you know, if you felt like in this example where numbers were so close together, then it would actually make sense to dive into the deeper calculation than just use range rule of thumb, since you would not get a good result from these data sets being so close to each other. But it's really just that idea of quickly, how can I calculate the standard deviation so I can make my decision based on that. Alrighty, so Chebyshev's theorem is kind of working with that idea of what data do we have and how it is dispersed, right? So remember we said within 2 standard deviations of the mean, 75% of your data values are going to be clustered between those 2 standard deviations. So again, they're kind of repeating a little bit about dispersion here, so you guys can read that. The less the data values are dispersed, again, the more consistent they are going to be. This is, of course, named after a Russian mathematician. I'm trying to remember, I have to always Google this name to get the pronunciation because I want to say Chevy, I think it's Chebyshev, even though it's S-H-E-V at the end. I think it's pronounced as Chev. You can actually YouTube the pronunciation because that's what I have to do. So basically, again, the idea is what percentage of our data is spread out between these standard deviations. So there's this little formula right here in this box. So they're saying the proportion of values from a data set that will fall within K standard deviation. So are you within 1 standard deviation, 2 standard deviations? For that matter, that value of K could be like 1.35. So if you are 1.35 standard deviations away from the mean, that's what that K value is going to be. So you actually have to put it into this little formula here, where it's 1 minus 1 divided by K squared, where K has to be a number greater than 1, and K is not necessarily an integer. So this is what they're talking about. K can be a decimal value. It doesn't have to be +2, -2, and stuff like that. So this is actually going to be that critical part of the Chebyshev's theorem, is remembering this little 1 minus 1 over K squared. And I think you have this in your little note card handout in there. Okay, so how does that formula work? So we're talking about within 2 standard deviations of the mean, 75% of our data value is there. So if you take that value of K and replace it with 2 in this formula, so you've got 1 minus 1 over 2 squared. Remember your K is 2. That would of course become 4. So that's 1 minus 1/4, which is 3/4, and 3/4 is the same as 75%. If you change that denominator to 3, so you should actually, right here in the second calculation, you can see when you change it to 3 and go through this calculation, within 3 standard deviations below and above your mean, we are saying 88.89 or approximately 89% of your data values are actually going to be clustered within those 3 standard deviations of your mean. And then here, they're actually just showing you that same calculation that we did with the range rule of thumb. So if you take the mean of your data set and add and subtract 2 standard deviations, so that's 2 multiplied by the standard deviation of 1.5, that will actually give you what the smallest value and the largest value at your standard deviation should be. So basically, Let me show this to you on a little distribution chart here. Okay. All right, so they are telling us, just let's do this on a horizontal axis. The mean, and I'm actually looking at this first part here with the variable 1 as a mean of 70 and a standard deviation of 1.5. Okay, so mean, and we don't know what kind of distribution this is, but let's say this is our mean, right? If I go 1 standard deviation above, that's going to be 70, and they told us the standard deviation was 1.5. So what is 70 plus 1.5? 71.5. If I went 2 standard deviations away, again, add that 1.5, and where are we at? 73. And I'm actually going to do it one more time for the 3rd standard deviation. Where do we go? 74.5. Very good. Now, if you are going below the mean, there we go. So it's 70 minus, right? Because you're going below the mean. So what's 70 minus 1.5? 68.5. And then we go 2 standard deviations, so again, subtract. 67. And let's do a 3rd one. 65.5. Okay, so look at those calculations they did. You were adding 2 standard deviations above and 2 standard deviations below. We're at 73 and 67, and that's your 73 and 67. So that's how they're showing those calculations to you. So basically for the 73, they're talking about, since you're going above, that's 70, which is the mean, 2 times the standard deviation. That was 1.5. And then this guy was the same calculation, but you are subtracting. Right? That's how you calculate these values if you are going to be 1 standard deviation away, or 2 standard deviations away, or 3 standard deviations away from your mean. Now, normally we don't go beyond 3, but again, it just depends on what kind of distribution you have, and do you have a reason to go beyond 3. I mean, you can obviously go till you get to 100% of your data values, right? So I mean, you can keep going, but typically you will see we'll do 1, 2, or 3 standard deviations, and then you can actually do numbers in between. Like I said, it doesn't have to be integers, it can be decimal values also. And then remember, this is not just for a symmetric or bell shape. This can be, and this is just a rough sketch, but this can be for a skewed distribution, because Chebyshev's theorem works on any distribution. It works on right skewed, left skewed. Remember, we had talked about J-shaped and reverse J-shaped and uniform and symmetrical. I mean, any kind of distribution, you can actually use Chebyshev's. But the idea is, if you have a symmetrical distribution, you will get more accurate answers if you use the calculations for the bell-shaped ones. But otherwise, in general, Chebyshev will give you at least a decent answer out of that. Alrighty, so you can kind of see how we did that same calculation here with 3 standard deviations, which puts us at 65.5 and 74.5. So you should be again able to verify that with 65.5 and 74.5 being 3 standard deviations away from your mean as well. Okay, so this would be something you would need to remember when you're working with Chebyshev's theorem, which is these 3/4 or 75% fall within 2 standard deviations of your mean, and at least 8/9 or 89% falls within 3 standard deviations of your mean. So what we are basically saying here, from 2 standard deviations, that's this here and this here, right? We are saying approximately 75% of our data values are falling from values of 67 to 73. When you go out 3 standard deviations, that's going from 65.5 to 74.5, you are looking at approximately 89% of your data values. So think about it this way. If from 65.5 to 74.5 is 89% of my data, how much is left which will be outside of it? 11%, yeah? But here's the thing, since this is not a symmetrical distribution, we don't know how much we have on each side. So the idea is I can have literally a small, less than 1% on this side, but I could have a big chunk of that 11% on that side, right? Or since this is left skewed, you could actually say this is where I'll have, maybe 1% of my data, but then 10% is going to be here. Because this is not symmetric, we cannot do an exact calculation of how much is going to be outside of that range. Now we know 75% within 2 standard deviations, we know about 89% within 3 standard deviations, but honestly, beyond that, we don't know what you're going to have. So with symmetric distributions, you can actually divide everything by half and get equal values on both sides. That's the beauty of symmetry, and that's not going to happen with Chebyshev. So be very careful when you're working through your homework problems where they're asking you to do Chebyshev's theorem calculations to figure out what percentage of your data is, because you cannot, unless they tell you it is symmetric or bell-shaped, don't make that assumption that it's going to be equal amounts on either side. Alrighty, and you can kind of see they have a similar example here. So within 2 standard deviations is your 75%. Within 3 standard deviations is at least 88.89 or approximately 89%. Okay, so just to see how we can use this theorem, you've got the mean price of houses in a certain neighborhood is $50,000 and the standard deviation is 10,000. So they want to know the price range for which at least the 75% of the houses will sell. So this is actually where they're asking you to find the lower and the upper values, right? So you're basically using the mean plus 2 standard deviations, mean minus 2 standard deviations. And again, remember, since they told us specifically to find 75% of the values, that's why you are using the 2 standard deviations, okay? So you kind of have to be careful about that. So basically they are saying that the 75% of all homes sold will range from the prices of 30,000 to 70,000. Obviously they're not talking about Colorado here, are they? At those kind of prices there. So again, guys, since they told us 75%, that's why we did 2 standard deviations above and below the mean calculation. Look at that second example there, travel allowances. So a survey of local companies found that the mean amount of travel allowance for couriers was 25 cents per mile. Their standard deviation was 2 cents. So they want us to use the Chebyshev theorem and find the minimum percentage of the data that will fall between 0.20 and 0.30. So first thing we have to actually figure out is how far away from the mean these numbers are. So they're taking the 0.30, which is this upper limit here, and subtracting the mean, right? So 30 cents minus 25 cents, you are 5 cents away from the mean. Your standard deviation is only 2 cents, right? That means this is more than 2 standard deviations away, isn't it? Because at 2 cents double, you would be at 4 cents, and this guy is at 5 cents. So you actually then take your difference between the data value and the mean, divide by your standard deviation, and that gives you how far away you are from the mean, or what's your standard deviation, which is 2.5. So now, since 2.5 is not 2 or 3, it's in between that, you have to actually figure out what percentage of data that's going to be. So this is where you bring that Chebyshev Theorem's formula, 1 minus 1 over k squared, where your k is 2.5. And going through that calculation, you can see you end up getting 0.84, right? 84%, which is actually telling you, since you're talking about 2.5, you are going to be right here in the middle of 2 standard deviations and 3 standard deviations. So you have to be in percent sense between 75 and 89%. And you can see that guy comes out to be about 84%. So then we would say 84% of our data values fall within the travel allowances of 20 cents and 30 cents for the couriers. Okay. Let's look at examples here for Chebyshev. Okay, how about we do number 31 here. So they're asking us to use Chebyshev's theorem, solve these problems for a distribution with a mean of 80, standard deviation of 10, and they want to know at least what percentage of values will fall between 60 and 100, and what percentage would fall between 65 and 95. So this is actually like example 12 that we just looked at. Okay? Okay, so the first thing we would need to do here, let me go ahead and write these numbers down for us. This is number 31. They're telling us the mean is 80 and the standard deviation is 10. For part A, they are asking us to find what percentage of values fall between 60 and 100. Okay, so where will you start with this guy? And look at example 12 on your handout and follow that. And you don't have to use both 60 and 100. The idea is they should be equally distanced from the mean. So if you look at the mean of 80, 60 is how many units away? 20. And from 80, 100 is how many units away? Yeah, so you can just pick any one of those values. You don't have to do it for both of them. So again, to keep it positive, let's start with 100 minus the mean, which of course comes out to be 20. Then you take that 20, divide it by 10, which is your standard deviation. 2. And this will be our k value, right? So if it's 2 standard deviations away, it's 75%. So if you remember that, then you don't have to go through the calculation. If you don't remember that, then this is where we would bring in that Chebyshev formula. So that would be 1 minus 1 over 2 squared, which is 1/4. 1 minus 1/4 is 3/4. Convert that to a percent, you have 75%. So we would say 75% of the values fall within 60 and 100. We were doing number 31. This next one was between 65 and 95. All right. So follow the steps for part A, or like you saw in example 12 in your handout, and let me see what percentage values you come up with between 65 and 95. So what does our k value come out to be? Well, if somebody's done anything more of it, you know, just remove that. What did we get for the K value?
1.5.
1.5, yeah. So if it's 1.5, which means it's less than 2, which means your percentage has to be less than 75%, right? So kind of keep that in mind. And for this one, you'll definitely need to use that Chebyshev theorem formula, which is 1 minus 1 over k square. K happens to be 1.5. And what is 1.5 squared? 225, 2.25. Are we getting that? 0.55555 repeating. Okay, so as a percent, okay, I don't know what happened. As a percent, what does that come out to be? 55.6 or 56%. If we're keeping it to whole numbers. So like I said, since you were at 1.5 standard deviation from the mean, the percentage should have been less than 75%, and of course, that verifies with that 56% approximate calculation. So again, we would say 56% of the values fall within, what was that, 65 and 95? Questions on this example? So this was calculating the percent, right? What percentage fell within those range of data values. Okay. Okay, how about 35? Americans spend an average of 3 hours per day online. If the standard deviation is 32 minutes, find the range in which at least 88.89% of the data will lie. Use Chebyshev. So now they're giving you the percent and asking you to come up with the data value. So this will be more like example 11 from your handout. So where do you start? So you've got 3 hours Standard deviation was 32 minutes. They're asking you to find the range for at least 88.89%. Do you have an answer?
For the first step,
Where would you start?
I did 100 minus 3
100 minus 3. And why did you do 100?
because that's, well, I don't know if we did the last problem.
Oh, that was because they gave us the data value of 100. Okay, so yeah, you won't be able to replicate that because this is a completely different type of problem. Okay, so where else can we start? Since they're not giving us that data range, we're finding the data range.
So I start by finding K.
Finding K. What were you gonna say?
I was gonna say, convert the hours and the minutes.
Very nice. Yes, that's the first thing you have to actually do is have the same unit of measurement. So 3 hours would be multiplied by 60, which would give us. Okay, so the mean would be 180 minutes and the standard deviation would be 32 minutes. All right, very good, Leah. Okay, now still the same question. Where do we get started? So how would we find K?
Well, you chose to do 0.8889 equals 1 minus 20.
Very good. Yeah, so you are now trying to find K. You are given the percent. So you are back to this formula. Now, our percentage, and yeah, convert that to a decimal. Very good, Joseph. Okay, so your equation solving, trying to get K by itself, where would we begin? Subtract 1. We're going to be left with negative 1 over K square equals, what do we get here? Very good. So since you have negative on both sides, you can, I don't know, think about it as multiplying by negative 1 so that you can get rid of your negative signs. Okay, now what do we do to get K square by itself? No, since K square is in the denominator, what do we got to do? Yeah, essentially you're multiplying by the reciprocal. Very good. So you would actually be multiplying by K square over 1. And that means we would end up with basically, since everything cancels out, you would have 1 left over here. And K square would now be multiplied with 0.1111. Okay, then what would you do?
Subtract 0.1111 from each side.
Very good. All righty. Joseph, what were you saying?
Well, you said subtract.
Oh, divide. Sorry, I didn't realize you said subtract. Yeah, divide, because you're multiplying K square with 0.1111, right?
Ah, yeah.
So opposite of multiplication would be division. Thank you. Okay, at this point, we're going to need our calculator because this is what we have. K square is now equal to 1 divided by 0.1111. So normally, this is where we would take a square root. When we take a square root, we normally get a positive and a negative root. but we know our k value is going to be positive, so we are actually ignoring or discarding the negative root. We're just going to stick with positives here. So that square and square root will cancel out. And then, like I said, our calculator should be able to help us out. So you are taking the square root of 1 divided by 0.1111. And that comes out to be
Yeah, 3.00015.
that's approximately 3. Okay, so we went through this calculation for a reason. 88.89%, if you go back and look at your handout, is within 3 standard deviations of your mean. So you could have actually used that. But here's the thing. What if they had given you a different number from 75 and 88.89? What if they said find within 82%, or at least 82%? Then what would you do? So you would actually need to go through this calculation. So 75 and 88.9, for 75, you use your k value as 2. For 88.89, you use your k value as 3. But if they give you a number outside of that for Chebyshev, this is going to have to be your process to find that k value. Okay. We're still not done. This was just part of the calculation. We still have to find our range, right? So how do we calculate that range now? 3 standard deviations from the mean. Phil, if you need to leave, I would not want you to be late.
I appreciate it.
Okay. So remember, this is where you take your mean. And then for the upper largest value, you take 3 times your standard deviation. And because our k came out to be 3, that's where the number 3 is coming from. And then for the lower one, you're doing the same thing, but with a minus sign. So our mean was given to us as, we converted it, what did we get? 180, very good. So please remember to use the 180 and not the 3 hours. And then you are adding 3 times your mean plus 3 times the standard deviation, which was 32 minutes. And then do that same thing with the minus sign for the lower limit, and let me know what you guys come up with. So for the upper limit of our range, 276, very nice. And remember, this is all in minutes. 1. All righty. 84 minutes. If you want, you can try converting them into hours, which would be dividing by 60, right? You're probably going to get decimal answers, since obviously we're not at round hour values here. Okay, so this was example 35 of basically finding what the 88.9 or 89% of the American population is doing. So we're basically saying they are spending anywhere from 84 minutes to 276 minutes being online, and that's about 89% of our population, right? Because 3 hours to me seems like a small amount of time. I mean, if I just consider myself, when I'm not in class, I'm in my office and I'm on the computer, right? I'm either checking my emails or making up my assignments, going through something. So I am constantly on the email. And now if you think about it, with our smartphones, I mean, we are always on the internet, are we not? So, I mean, 3 hours definitely seems like a lower end, but when you start considering, okay, if I go from this range to this range, then yeah, it makes sense. You would have a standard deviation of 3 taking you from 84 to 276. Questions on this exercise here? All right, guys, we have one tiny bit left in this section, which is what, 3.2. So we just have to talk about the empirical rule, which will be for that symmetric bell-shaped curve, and then we'll get into 3.3 and 3.4. And I don't know if that's going to take us more than next class period. And if it does, maybe a little bit of the following Monday. But you should prepare for chapter 3 exam a week and a half from today, basically. So Wednesday of next week. Yeah, so that's what I'll put the due date for your homework also. Okay, and if you have any questions, please let me know. Have a wonderful day. And I will